Okay, so what I'm focusing on in the second half of this tutorial is modelling things in PDDL. In particular, how we do richer problem models, so moving away from just the propositional representation we heard about in the first part into more complex models involving time and numbers. So it's going to be half pragmatic, how do we model a certain problem in PDDL, and also half sort of understanding what extra features and a little bit of what's going on behind the scenes in order to support that. So the planning fundamentals, just to recap, starting from some initial state, using some actions we have available, we want to reach a goal, and we want to do it quickly or cheaply or somehow. So there's some quality measure there which is you have in mind. And the way we model things in the planning, as was mentioned in the first half, is we split things into two. We have the domain and the problem. So the domain stays the same in a certain class of problems, and the problem file is a specific instance that you're concerned with at this given time. So the actual constructs that we use to write a planning problem, well, in the domain file we have types. So we say we have trucks, we have packages, we have cards, we have oranges, which can be a subclass of fruit and so on and so forth. So we have a typed language there. We have predicates, which allow us to define relationships between these typed objects. And we have functions, which are numeric quantities in the world, which I'll be coming back to a little bit later. And we can have constants, so things like north and south and east and west. So things which are going to appear in every problem, we can actually put them in the domain file as constants. So in the domain file we define the types, and in the problem file we would define the typed object. So that's being specific, so saying which specific trucks or packages or cards we're looking at in this problem. In the problem file we then will have the initial state, which is some predicates and some function values specified using these typed objects. So this is where the propositions come in, so we would define some propositions, and the class of the propositions we can define are those which use our predicates and use our type objects. In our domain file we then have the action schemata, so there's sort of the templates of the actions, so things like we can load a package onto a truck if the two are in the same place. In the specific problem we're looking at, we'd then be able to say, well, we have this template here, we'd then be able to get what's called a ground action, which would say, if we have the propositions, then we can instantiate that action and get its effect. So that's again how we can have one domain file which defines a template. When the planner is then trying to solve one specific problem, it will then create instances of actions which have those schemata. And then the final thing in the problem file is the goal. So we would say get from this initial state to that goal using the action defined by these templates and using these are the objects in the world. And the other thing in the problem file is the metrics, or our quality measure. So this doesn't actually need to be the same in different problem files in the same domain. You can have, for instance, within logistics, and some problems you might be concerned about minimizing the total length of the time it took to do things. In other problems you might have a cost measure to do with fuel consumption. In other problems you might be trying to minimize the number of different trucks you have to use, for instance, if you're doing resource constrained planning. So you can change all this stuff and keep the domain stuff the same. So here's an example of, it's a nice problem, which is, it's nice in many ways, but one nice thing for the purposes of this tutorial, this only needs the sort of PDDL and the sort of planning models which you saw in the first half of this tutorial. And it's called the Scanalyzer domain. And it comes from a paper from ICAPS 2010, where it's looking at managing the operations of a greenhouse using a planner. So we have this large hydroponic greenhouse, where on the right-hand side here, we have these batches of plants are on conveyor belts, so A, B, C, D, E, F. And these arrows indicate the directions in which the conveyor belts move. So these at the top will move to the left, and these at the bottom will move to the right. And then the ones at the side, you can see sort of form this circuit which goes round anti-clockwise. If you move a batch of plants round anti-clockwise over here to the left, it goes into what's called the imaging area. So we can take images of the plants to measure things like the chlorophyll levels, to measure how well they're growing, and so on and so forth. So you can just essentially large-scale scientific evaluation of different crop production methods, or if you're actually trying to grow crops, then you can monitor how they're developing over time. Maybe you need to tweak the nutritions which are going into the hydroponic substances. And this is actually a real product. So this is, you can see, this is the greenhouse that was on the previous slide. We have 3 sets of conveyors here, and we have 3 sets of conveyors over here on the right. So here we have the plants on the conveyor belt, and they're moving around there. And you can see, that's the screenshot I took. So they're moving around this outside ring here. So that's, if you remember, that was batch F on the bottom there. So that's now moving around anti-clockwise. You can see the greenhouse has all the necessary equipment that needs to monitor the plants, so to do with RFID tags and things like that. There you go. So they're all individually labelled. They're dealt with in batches, but they're individually labelled just to make sure we know which plant we've measured and so on and so forth. Then they go into this imaging area, one at once. So they go in there, they're fixed into place, and then some sort of complex analysis is done. So it's proper high-tech stuff here. And the planning problem is essentially how do we move these plants around in order to be able to monitor their growth. So we need to analyse the plants, and we have this arrangement of conveyor belts. How do we actually then shuffle the plants around so they've all been imaged, so they've all passed through this imaging area, and then we want to get them back to where they started, so we have these consistent growth conditions. If you want us to model this as a planning problem, well, what types and predicates are we going to use? So let's start with fundamentals. Well, we have conveyor belts, so we're going to call those segments. So you can imagine we have 6 segments, A, B, C, D, E, F in our problem. And we have the batches of the plants in there. And as I mentioned briefly, as an operational constraint, we move plants a batch at a time. So we move everything off one conveyor belt from where it is to somewhere else in the greenhouse. What predicates are we going to use? Well, a batch of plants is on a given segment. So it's just like in the blocks world domain, where a block will be on another block. Well, here, a batch of plants is on a segment. So a batch of plants as a whole is on some conveyor. And we also have a predicate to say whether or not a batch of plants has been analysed. And then to link together these segments, we have these things called cycles. I'll illustrate those with an example. So this is the initial state of the problem, and we have several cycles here. And if I go back to this figure we started with in the bottom right, each opportunity we have to move these plants, for instance, we can move all of these plants from A down and to the left and then down here, and then we can push them onto this D. But if we're doing that, then the plants which are on D have to go somewhere, so they would come back up here and they would take the place of the ones with A. So that's the sort of swapping operation we can do. So any pair on here where we have one going to the left and one going to the right, well, that leads to the cycle here. You can see these are enumerated all the possibilities. And then we have this one cycle with analysis as a special case, which is A to F. Because you remember, if we push something from A, it goes to the left, it goes to the imaging area, and then it comes back into the bottom of F. And of course, anything that was on F will have gone down the side here, back up, and then gone to A. So the goal of the task, so not the goal yet. So this is the initial state, and these are the initial positions. So batch 1 of plants is on conveyor belt A, batch 2 of plants is on conveyor belt B, and so on and so forth. The term Amanda mentioned in part 1 of the tutorial was static facts. So these are things which never change. So we never change the actual mechanics of the greenhouse. We never change which direction the conveyor belts can go and so on and so forth. So those facts are static. But where things are, that's not static. So that's essentially what the planner's playing with. It's moving these things around, and it's going to add some analysed facts as well to note when things are going through the imaging area. So the actions, well, the simplest action is just swap 2 things around. So this is called rotate, so it swaps 2 batches of plants. It takes some typed parameters, so we have some segments, so some conveyor belts, and we have some plants. These batches of plants have to be on those conveyors. And we have to have this cycle relationship between those 2 segments. So it has to be one going to the left and one conveyor going to the right. So we have to be able to swap them around. If we apply this action, essentially we do this swap. So batch 2 is no longer on segment 2, and afterwards batch 1 is on segment 2 and vice versa. So you can see we essentially swap. So batch 1 moves from segment 1 to segment 2 and vice versa. And then this thing here at the bottom, I'll come back to this in a minute, but you know, but we've said this operation has some nominal cost of 1. And in this problem, it means it takes, essentially, it's 1 time unit. We're trying to do things quickly. So you can say, well, this is going to take 1 time unit, so our cost measure is going to be time. We'll just say we're going to increase our cost by 1. Our action that actually analyses the plans is very similar to the one on the previous slide, but instead of just having cycle 2, we have cycle 2 with analysis. So it has to be a swap where if we swap them around, they will pass through the imaging area on the way. So there's only one of these in this problem. It was A at the top and F on the bottom. If we swap A and F, then what wasn't A will get moved to the left and will come down through the imaging area and will come back on the bottom. Now if we do this, well, 2 things to notice. First, we get this analysed fact, so we've now analysed a batch of plants. And the second thing is this has cost 3, so this is more work than just swapping 2 batches around, because you've got to allow time to lift. Remember the video, you've got to lift all those plants up, take images off and get the lighting right and so on. So that takes more time than just doing a swap on 2 conveyor belts. So our goal, moving from our initial state, using these actions, what are we trying to do? Well, we're trying to have everything analysed, and then we're trying to return things back to their initial positions. Now, if you didn't care about this latter part, you just have a goal which is to say we've analysed everything. So with this second part, returning to initial positions, it's an extra complication. So what you might see plans doing, if we were to find plans for this domain, is that they would have to do some cycles with analysis, and then at the end of the plan, having analysed everything, just finish off with 2 or 3 extra cycles just to swap things around to get them back into the order in which they started. And because we have this extra line written at the bottom of our problem file, which says we've gone to our metric, our quality measure is to minimise the total cost of the plan. Well, remember, rotating 2 segments, so swapping 2 segments had a cost 1, rotating and analysing 2 segments had a cost 3, so more or less, if possible, the plan is going to prefer to use rotate actions, so there's a 3-to-1 ratio there. If there's 2 ways of doing things, then it's going to go for the one with the rotate, rather than rotate and analyse. So I found this planner, and I got this nice little screen plan here. Exactly as I suggested, it starts by doing some analysis operations. To do the other analysis operations, it ends up having to do some rotations, so it has to swap things around a bit, then it can do some more analysis and so on and so forth. This is the last analysis action here. So at time 0.010, it does our last analysis action, and then after that, to get things back to where they started, it's got to do some rotation actions there. So this analysis action will lead to some batch of plants ending up on segment F, but that batch of plants didn't start at segment F. We got to do the extra rotate to essentially, it's a bit like working with a sliding block puzzle. You've got to push things from one conveyor belt onto another to get everything back to where it started. Well, does this stuff actually work? We have questions, some people ask questions after the first tutorial about the performance of planners. So this is a table comparing various relaxation-based planners, so delete relaxation-based planners from the international planning competitions at IPC, and just comparing those to essentially a planning-like approach that had been written by hand. So an inadmissible heuristic, which just works on this one problem, so something a bit like Manhattan distance, you might imagine, which just works for the 15 puzzle or the 8 puzzle. Well, you can write a heuristic that just works for Scanalyzer, and you're going to use it with A star. So if we look at this table here, and we look at the quality of the plans produced, so this is the cost of the plans, well, you can see depending on the layout of the greenhouse, In layout 1, it's neck and neck. There's no difference between using a domain-specific solver and using a planner from the planning competition. Over here in layout 2, well, the domain-specific solver has the edge on the quality up to size 16 of a problem, but then it stops working, whereas the planner continues going. And then over here, on the far right in layout 4, you can see that this planner on size 8, the planner is able to get a cost of 30, whereas the domain-specific solver will have a quality of 32. And that's because it's using an inadmissible heuristic, so it's not guaranteeing that it will find the optimal plan. So these little stars mean it was optimal. So you can see in this case, because it's not using an inadmissible heuristic, it's finished, it's returned a solution, but that solution isn't optimal. And we know it's definitely not optimal because A, a planner has found a better one, and B, an optimal planner has found a solution. In this case, if we look at the paper, that lets us know that that is indeed the best possible planner. You can see these larger ones at the bottom right-hand corner of the table, this triangle here. These numbers don't have stars by them, so these haven't been proved optimal. It may be that, for instance, in layout 4, size 24, there is a solution of cost better than 128, but with the planners we have, 128 is the best we've managed to find so far. Maybe it might be optimal, but proving optimality is much harder than finding a plan which happens to be optimal. You've got to do that extra proof step in there. So that might be optimal, we don't know yet. So that's the Scanalyzer domain. And as I said, the nice thing about it is that it just needs the PDDL, which you've already heard about so far. Yes?
So maybe I missed this, but the size here is the number of batches now that you have? Or?
Yes, it's the number of batches and conveyors in the greenhouse. So they go in twos because they're added in pairs. So you add one conveyor at the top and one at the bottom.
So it's always one batch per conveyor?
Yes. So that's everything starts fully loaded. There's no slack in the system because we want to get as many plants into there as possible. And then the different layouts are. So I've shown one layout where you have the imaging area on the left. You might imagine that you could have an imaging area in the middle and then have sets of conveyors either side of that. So you can do different layouts, and that's what they are there. Okay, so Scanalyzer, it shows that actually sometimes you just need simple planning languages based on propositions, essentially predicate-based logic. And if you can get away with using that, if that gives you a model which is realistic enough to be able to solve your problem, by all means do that, because you have plenty of planners to choose from. There's a lot of essentially fundamental planning research looks at these propositional problems. But sometimes we need more than that. So sometimes we can't write a model which is exactly what we want by referring just to propositions. And one way in which we can extend PDDL is by adding numbers to it. So instead of a precondition just being this fact is true, we can actually have a precondition saying this formula over some values of some numeric variables which we can store in our state alongside the proposition. Well, this formula also has to be true. So I'll do this slide from the bottom going upwards, so I'll show you some examples first. So we might say that the amount of fuel we have is greater than or equal to 5 times the distance between two places. So say this was the number of litres of fuel we're going to use per 100 kilometres, and this is how many 100 kilometres there are from one place to another. Then essentially that's saying we have enough fuel to make that journey. Or we might say we have a truck and we have some barrier, and then to be able to move the truck into the depot, then the height of the truck has to be less than or equal to the height of the barrier. Or at the bottom here, say we want to ship an order to a customer and they've ordered 3 widgets, then we might say the number of widgets we have produced is greater than or equal to 3 for us to be able to then ship it. So in a general form, PDDL numeric preconditions comprise some comparison operator. So here, for instance, greater than or equal to, less than or equal to, or it could be greater than and less than, or just straightforward equality. And then a left-hand side and a right-hand side is specified for that comparison operator. Now because PDDL is written in prefix form, it looks like they're both on the right hand side, but you can imagine if it was an infix form, here the left hand side is fuel, and the right hand side is 5 times the distance from 2. And then these components which are on the left and right hand side, we can use plus, minus, times and divide. So there's no trigonometric operators there, there's no square root, there's no sine, cos, so on and so forth. It's quite a useful language, and in principle, PDDL, numeric, preconditions, anything you can write in this language, you can write in PDDL. So preconditions are just one side of the coin. On the other side, we then actually need to be able to change the values of these variables. Now, increased total cost 1 you've already seen, or increased total cost 3, is perhaps the simplest form of numeric effect. In general, we can say numeric effect comprises some variable they're going to change, how they're going to change it. So the keywords, language keywords, are things like we're going to assign it some value, or we're going to increase its value, which is like doing plus equals in Java or C, or we can decrease its value, we can multiply it by some amount, we can divide it by some amount. And then, having specified the variable and how we're going to change it, we specify the formula that essentially will form the other part of this update operator. So for instance, we're going to decrease the amount of fuel by 5 times the distance between one place and another. You'll notice this is paired with the precondition on the previous slide. So the previous slide I said the amount of fuel we have is greater than or equal to 5 times the distance from 2. We could then have that as a precondition of an action, and then as an effect of the action, say we're going to then decrease the amount of fuel. So more or less that precondition saying we have enough fuel and we apply the action, we've used that fuel. And then think about the number of widgets. We can have an action that will increase the number of widgets by the capacity of some production machine, or if we have some battery, which we're doing, for instance, some Martian rover planning, we might have some action for recharging in the sunlight, but at the end of it, we'd say we're going to assign the battery charge back up to the maximum capacity of the battery. So these are our 3 sorts of operators. They all take some variable we're going to update, so fuel, number of widgets, or battery charge, and they all state how they're going to be updated. So it can be some function, so 5 times distance, or it can just be whatever the value some other variable happens to hold in the current state. Now, I said in principle, it was a bit of a weasel word. In practice, most planners assume that we're working with linear formulas, so they're written in linear normal form. In other words, for preconditions we say that some weighted sum of the variable values in the current state is either greater than or equal to some real valued constant. So we assume that preconditions can be translated into LNF. You don't necessarily have to write them in LNF in the planner, but we assume they can be translated into LNF. It's a fairly easy process to automate if it can be done. Similarly, we assume that effects are linear, and to guarantee linearity, we straight away say you can't do the multiply by some constant or divide by some constant, for instance. We restrict ourselves to increasing or decreasing, so adding or subtracting, or assigning a replacement value to a formula which again is in linear normal form. So some variable is either increased by, decreased by, or assigned. The product of it's a weighted sum of the variables values in the current state plus a constant. So everything on the previous slide, conveniently enough, can be written in this form, and it's an easy enough process to automate. So here's an example problem where we need numbers, and it's quite compelling being based in London and working with computers which notoriously need a fair amount of power to keep them going. So this is a map of the UK, if you're wondering what the country you're in looks like at the moment, and London is here. And from a power distribution point of view, London's quite interesting because there's very little power generation in London. All the power generation is around London. You can see these blue lines here. These are all power transmission lines. And you can see it's kind of a radial structure. But the power generation is all somewhere around London, so out of the city where land's a bit cheaper. And then there's all power lines which come into the capital to supply power to it. The case which we looked at when building the substation domain, was Grendon substation, which is just northwest of London there. And essentially, we've got power coming in from various sources, and we have a substation there, which has various pieces of equipment on site, and its task, or the task of planning, is to operate that equipment so that the voltage coming into London lies within some acceptable range. So say nominally the overhead voltage lines run at 132 kilovolts, then we want to operate the equipment in the substation such that that voltage coming out is 132 kilovolts plus or minus 5%. In terms of used in the industry, that we normalise by 132, and we're saying we're going to be between 0.95 and 1.05 per unit volt. So you normalise everything to 1, and so we're in the range plus or minus 5%, so 0.95 to 1.05. The thing which makes it an interesting problem is that our electricity demand is not constant. If electricity demand was the same, you just dial the power generation plants to roughly what you need and sit back and enjoy. In the UK, we have this slightly odd phenomenon for people who might have travelled from further away, that we use a lot more power in winter than we do in summer. So this is the worst case for winter, this is the best case for summer in terms of power demand, and you can see there's a factor of 2 or so difference there. And it's because we need heating in winter. I was working with a colleague in Arizona who took a lot of this because their power demands go up in summer because of all the air conditioning. So it's a slightly opposite situation to what you might be used to, but actually at the moment the air conditioning in buildings do very nicely indeed. So given the fact that the demand varies across the day, we need to come up with a plan that, as this demand changes, will operate the equipment in the substation to be able to keep the output voltage within an acceptable range. And the two main pieces of equipment in the substation that we have to do that are mechanically switched capacitors, which can either be switched in or switched out, so they're either connected to the power line or they're not. If you know capacitors from electronics, imagine the little capacitors you see on a circuit board, but the size of a car. And they take power in from the line on the upswing of the sine curve with AC, and then they release it on the downswing. And the net effect is roughly, you could say, if we're going to switch in a capacitor bank, it will increase the circuit voltage by 0.02 per unit volt, so about 2%. It's a ballpark figure. And then the other piece of equipment are transformers. So the transformers where you can change the tap settings, so you can change the ratio of the windings between the primary side of the transformer and the secondary side of the transformer. So as a rule with an AC transformer, if you have twice as many turns on the primary side as you do on the secondary side, then you'll halve the voltage going across. If you can change that ratio, you can change the voltage on the secondary side. So we have large transformers which typically have about 30 positions, so you have a choice of 30 tap settings. It's usually some nominal value, is plus 10, minus 20, and each one of those steps will have a small effect on the circuit voltage in the region of, say, 0.008 per unit volt. It's a ballpark figure. The actual value is more complex than that, but I'll come back to that point a bit later on. So how are we going to model this? Well, we need to have variables in our state. The PDDL term for variable is a function. So we need to know what the voltage is on each circuit. So this nominal 1 per unit volt figure, or 0.95 and 0.05, but we need to know what that number is. For the transformers, well, if they have 30 tap positions, we need to know what the current tap position is, because we can't allow our actions to use tap settings on the transformer that don't really exist. If it can all dial it up to the 30th position, we need to have some precondition that says you can't dial up the setting of the transformer if you're already at position 30. Similarly, you can't dial it down again if you're already at position 0. And then for each piece of substation equipment, so either a capacitor or a transformer, we need to know what the effect of operating that equipment has. So for a transformer, what is the voltage change per step? Every time you change the tap position, what happens? And for mechanically switched capacitor, what is the voltage change when we switch it from being on, so being connected to the circuit, and being disconnected from the circuit. And I'll approximate it to linear for now, because as I've mentioned, we need to assume that we have linear effects on actions. So here's what the action would look like for stepping up the transformer. You might have guessed what some of this would look like by now. So here's the precondition I mentioned. The number of turns on the transformer has to be less than the maximum number of turns. So say the maximum number of turns is 30. If that's 29 or less, we're golden. We can step the transformer up. This second bit here, you can see that the transformer has to be connected to some circuit. Now this is a static fact, so this is encoding the topology of the substation. And the reason we need to know the relationship between the transformer and the circuit it is connected to is because if we apply this action, it has an effect. It's going to increase the voltage on that circuit by 0.008 per unit volts. It also has some other effects, so it increases the number of turns on the transformer. So we recorded, but we've now stepped the transformer up a notch, so we've got less headroom if we want to step it up further. And again, we're doing cost minimization, so we want to increase the total cost of our operations by 1. Because really you want to minimize the wear and tear on the equipment. You want to try and find a cheap way of operating the equipment so that your voltage is at the level you want, but you've not spent too much money. Now, what about time? Well, the demand changes over time. It changes throughout the day. So fundamentally, in our plan, we need some model of time. We need to be able to say, when is it that you need to switch this transformer step or switch this mechanically switched capacitor into or out of the circuit. And this problem, we can use a discrete model of time. We can divide the day into 30-minute intervals, and then we say, at each 30-minute interval, are we going to do something or are we not going to do it? And the way we can do that in the planning problem model is just to have an action called advanced time. So it's a dummy action, and it has the effect of changing the voltage on the circuits by what would happen in reality when the demand changed at that point. So if the demand is going to go up from say midday to half past midday, then advancing time at that point would decrease the circuit voltage. If the demand goes up, the circuit voltage goes down. If the demand fell, then the circuit voltage would go up. And the other useful thing that advanced time does is, so far I haven't shown anything which checks that the voltage is in range. Well, at advanced time, we can get a pair of preconditions and say you can only advance time if the voltage is within this range of 0.95 to 1.05. So you can then imagine that the plan would comprise some transformer stepping or MSC actions, and then advance time, and might be able to advance time a few more times. Then you have to do some more actual actions, and then you could advance time some more, and so on and so forth. And the goal is to have managed to advance time to midnight. So if we're doing planning for the day ahead, once you've managed to advance time enough to go down the clock and get back to midnight, you know you've planned a day's operations. So here's what advanced time looks like. It has this pair of preconditions, so we can only advance time if the voltage is greater than or equal to 0.95 and it's less than or equal to 1.05. This is where the voltage on the circuit changes due to the change at that time. That might be a negative number, so just because that says increase, it doesn't necessarily mean that that voltage is going upwards, because if we increase by a negative number, it's going down. This relationship here is an idiom in PDDL. So these are two type parameters, which when we're going to plan with this, we'll have to say we have two objects. So we have an object 3 AM of type time and an object 3:30 AM of type time. And then we can put in the initial state this static fact that says 3 AM comes before 3:30 AM. Why do you need to be able to say that? Well, we need to change which time step we are at after we execute this action. So T1 comes before T2, and when we apply this action, we are no longer at time T1, and we are at time T2. And you can see, if we put the goal to then get the current time back to midnight the next day, then we've managed to advance time throughout the day. And if we've managed to advance time throughout the day, then necessarily we have checked this pair of voltage conditions each half hour throughout the day. How are we actually going to plan with this? Well, let's recap the heuristic. So the relaxed planning graph heuristic was based on propositions and this idea of ignore and delete effects. So for instance, if we took this action move, which takes some object from one location to another, we would just say we're going to ignore that delete effect here, but not at x from. So we're just going to keep this positive effect. Well, what do we do now we have numbers? Let's say that move action also used a bit of fuel. So we could say we'll have a precondition that the amount of fuel is greater than or equal to 1, and we're going to have an effect that we're going to decrease that same amount of fuel by 1. Well, if we strike out that fuel usage effect, is that a relaxation of that action? You're way ahead of me. So let's come back to advanced time. The annoying thing about advanced time is we want it to be big and we want it to be small. We want it to be big because we want it to be bigger than 0.95, but we want it to be small because we want it to be less than or equal to 1.05. So if we ignore the decrease effects, well, that's quite good for the one which requires it to be greater than or equal to some amount, because if we ignore the decreases, then the voltage on the circuit isn't going down. So essentially, we'll pretend that actions can't make the voltage go below 0.95 anymore. However, on the other side of the coin, ignoring decrease effects is bad for the second precondition here, because actually, if we suppose the voltage was 1.1, then we want those decrease effects because we want to go 1.1, 1.09, 1.08, etc., etc., until we get to something which is back to being less than 1.05 again. So it's slightly annoying. We can't just say arbitrarily that decrease effects are the things we want to ignore, and also because, as I said, if you have a negative constant but you decrease by a negative amount, you've increased anyway, so it's not even obvious there. So the solution for the purpose of the heuristic is we're going to be really optimistic. The relaxed planning graph heuristic is all about being optimistic. So we're going to keep an upper and a lower bound on each variable. And we say if you're going to decrease the value of a variable, you don't change the upper bound, but you do change the upper bound. You do change the lower bound. And similarly, if you're going to increase the value of the variable, you don't change the lower bound, but you do change the upper bound. So you can eat your cake and have it. So if you're trying to get the voltage down, then you can say, well, this decreasing voltage effect, that's fine. We'll accept that and use it to get our lower bound down. But we'll pretend it doesn't do anything to the upper bound, because the upper bound we're trying to keep it high. And then we can relax the preconditions by being optimistic about which of the upper bound or the lower bound we use for looking at the specific precondition, picking the one which makes our life easy. So for instance, fuel greater than or equal to 5. So for this one, use the upper bound, right, because bigger is better. If we want to have, for instance, that the weight limit on the bridge is greater than or equal to the weight of the truck, then we can try and make that true optimistically by taking the upper bound on the weight limit on the bridge and the lower bound of the weight of the truck. If we take those two, essentially, the thing on the left you want to be big, the thing on the right you want to be small, that's going to make it more likely that your greater than or equals to precondition is true. And for the voltage constraints, well, one of them you would use the upper bound for. So if we're trying to get the voltage greater than or equal to 0.95, we would use the upper bound. If we're trying to get the voltage less than 1.05, we'd use the lower bound. So even within the same action, you can use both the upper and the lower bound. That's how optimistic it is. More formally, if you recall that preconditions are written in linear normal form, they are the weighted sum of our set of variables greater than or equal to a constant. And we can say that if our weight is positive, then we're going to use the upper bound on the associated variable. Otherwise, we're going to use the lower bound on the associated variable. Probably most easily explained with an example. So this example here, so is the weight limit on the bridge greater than or equal to the weight on the truck? Well, let's turn it from prefix form to something which humans will like to be, and put it in italics and time new own, because that's what you do with arithmetic expressions. We can rewrite that in linear normal form by pushing all the variables over to the left-hand side. So we end up with limit minus weight is greater than or equal to 0, so 0 is our constant in this case. We can rewrite that again, we've still not changed anything. It's saying 1 times limit plus minus 1 times weight is greater than or equal to 0. And now we can use our rule here. So if the weight is positive, we use the upper bound. Otherwise, we're going to use the lower bound. So what I sort of said informally on the previous slide was you would use the upper bound on limit and you would use the lower bound on weight. Well, that's exactly what we get more formally. So you can see that if the upper bound minus the lower bound is greater than or equal to 0, we can say in the heuristic, for the purposes of relaxed planning, we would say this precondition is satisfied. So as preconditions, we also have numeric effects, and we need to think about relaxing those as well. So is decrease V by W a decrease or increase effect? Now, you've already preempted me there. Well, it depends on the value of W. So if W is greater than 0, then decreasing V by W will decrease the value of W, will decrease the value of V. If W is less than 0, then we're decreasing by a negative number, which is the same as increasing by a positive number. So what do we do in the heuristic? Well, this variable here, as with all other variables, it has upper and lower bounds. If it never changes, its value might always be, say, minus 3. But say we're going to change the weight of the truck by the weight of the cargo which is currently loaded onto it, then that cargo level will change depending on what actions we apply in the plan. So the solution, when we're trying to work out what the upper bounds are in the heuristic, so we're going to apply an action, and we want to know, well, what's that going to do to our variable bounds? If the upper bound on this right-hand side here, so if the upper bound on this variable W is greater than 0, and it's a decrease effect, then we know, okay, we're decreasing by a positive amount, so we're going to decrease our lower bound on V by the upper bound on W. So that's going to give us the biggest possible decrease. So we're going to decrease V by as much as we can, so the current upper bound on W. Otherwise, well actually not otherwise, in addition to this, because W has an upper and lower bound, if we have a minimum value of W which is less than 0, i.e. if in fact, if we pick and choose, we can flip this around and effectively make it an increase effect by saying we're going to decrease by a negative number, then we will decrease the upper bound by this lower bound. That seems slightly backwards, but don't forget that this is negative. So effectively, we're going to decrease the upper bound by a negative number, or in other words, we're going to increase the upper bound. So this is very optimistic. We will take whatever value we like, and in fact we will take both. So simultaneously we might have one action that both makes a variable bigger and it makes a variable smaller by picking and choosing which value W it's going to take as input. If you want to have more than one variable here, so not just W, well, as in the previous slide, you can have a weighted sum and you put the lower bound and upper bound values into that. You end up with a maximum possible value and a minimum possible value, and then you reduce it to this situation here. So that's the relaxation. How do we actually get a heuristic from that? So it requires a remarkably small modification to the relaxed planning graph that you already saw in the first half of this tutorial. So just to recap, in the propositional case, fact layer 0 is our current state, so the state we want to find a heuristic value for. Action layer 1 is all the actions which are applicable in that state, so in this case all the actions that are applicable in fact layer 0. And then fact layer 1 is whatever we had in fact layer 0 plus all the positive effects of all the actions in action layer 1. And in the general case, fact layer I is all the facts from layer I minus 1 and the union of all the effects of all the actions in layer AI. So that's the propositional case. In the numeric case, then instead of just recording facts in fact layers, we also now record these upper and lower bounds on the value of each variable. So in fact layer 0, Well, we haven't done anything yet, so actually the maximum value in fact layer 0 of variable v is the same as the minimum value, which is actually the value it holds in the state we're evaluating. So if we have 10 units of fuel, then in fact layer 0, the lower and upper bounds of the amount of fuel we have is 10, because we haven't done anything yet, so that hasn't changed. What we then say in the next fact layer, the amount of the value of v, the upper bound on v, is whatever this upper bound was in the previous layer, plus all the ways we can possibly increase it using actions from the previous action layer. So it's taking all the possible increases, adding them together and saying, right, let's be optimistic, it's as much as we had before, plus the biggest possible increase we can get, and that's going to give us our new upper bound. And the same idea, our new lower bound is the lower bound we had before, plus the biggest possible decrease we can make on v using the actions in the previous layer. And again, bear in mind that one action might both decrease and increase v, but that's okay, because at this first stage here, when we're trying to get increase effects, we would get its biggest possible increase, and then when we wanted to get the lower bounds, we would get its biggest possible in magnitude decrease, so its smallest possible number there. To give you an idea of what this looks like in practice when we're going to expand planning graph, here's a simple little problem. We're trying to get these items of cargo from here over here. We have, in our store, we have 1 unit of cargo to start with, so the lower bound on the amount of cargo we have is 1, and the upper bound is 1, because we haven't done anything yet, so those values are the same. The amount of cargo we have over here at our destination site, that's also between 0 and 0, because we haven't done anything yet. We don't have anything on the lorry. I should say, for people who aren't British, a lorry is a truck, and this lorry is at the store. So we have a proposition and we have several variable bounds there. Okay, so let's expand this planning graph. Well, we have some actions which we can apply. So these are the actions whose preconditions are satisfied in the first fact layer. So we can produce some stuff. It's an action which says we're going to increase the amount of produce we have in our store by 1. We can load some produce onto our truck, and we can drive our truck from the store to the site. So because the truck's at the store, we can drive it to the site. So this gives us a new fact layer. You can see now the truck's in 2 places at once. The amount of goods we have in our store, well, that's increased on the upper side. The upper bound of it is now 2, because we say, well, we can have what we had before, which was 1, plus we've now produced some goods with this produce action, so now the upper bound is 2. But the other thing we could do is this load action. So if we load some goods from our store onto the truck, we would decrease the amount of goods in our store and increase the amount of goods that were on the truck. So you can see that the amount of goods on the truck on the upper bound is now 1. The lower bound is still 0, because we don't have any way of decreasing the amount of goods on the truck. So we would ignore the fact that you can increase it by 1, because that's not relevant to the lower bound. We'd only look at the increase by 1 for the purposes of the upper bound. And the sites stay the same because we haven't got to the site yet. In the next action layer, where we can do several things now, we have all the actions we had before, but now we also have these unload actions. So we can unload our goods from the truck, we can unload them back to the store, because we're at the store and we have some goods in the truck, or we can unload them at the site which we've now driven to, because we're now at the site as well. And if we do that, well, these are our bounds here. And the interesting thing is that you now note that we can actually get negative amounts of goods. You can simultaneously be in the store to unload goods at the store, and be at the site to unload goods at the site. I mean, it's nonsensical to say you've got -2 amount of goods in your truck anyway, but this is what the relaxation allows. And the key thing is, if our goal was to have 1 unit of produce at the site, we've now done it. We didn't actually need to produce the goods in this specific example, because we started off with some So relaxed plan in this case, if we just wanted to get some goods to the site, then we would drive to the site and then we would unload the goods at the site, and we could do that there. If we just expand the planning graph a bit further, just to reinforce this idea of what preconditions are satisfied, what actions are then applicable, we would then get these actions here. So there's one more action here, which is applicable, which is loading goods at the site. Now you and I would know that it's not something you'd ever want to do. If your goal is to get those goods to the site, then loading them back onto a truck and driving off is counterproductive, but the domain does allow it, so it does appear in the planning graph, and because we now have a way of loading goods onto a truck at the site, we can theoretically get a negative amount of goods at the site too, because the lower bound on the goods at the site before was 0. Now we have a way of decreasing the amount of goods at the site, so that our lower bound is now -1. So even though you get these negative values, and even though things go a bit crazy and it looks like junk, it's actually remarkably good heuristic in a wide range of problems. I'm not going to go through solution extraction to keep things simple, but it's the same basic idea as in the propositional case. You work backwards from the goal, but now we might need to say, if we have this numeric precondition, then we need to choose some actions that increase the values of the variables or decrease the values of the variables in order to meet that numeric precondition, and then the preconditions of those actions get pushed back. So remember gn, gn-1, gn-2. It's the same idea, but you've got to pick actions both to meet the propositional preconditions of actions and to meet the numeric preconditions of actions. One thing I mentioned is linearity. Well, why are we so obsessed with linearity? Because unfortunately real life isn't as linear as you would like it to be. Well, it comes back to this issue, which in the propositional case you met, of when can we stop expanding the relaxed planning graph? Well, we can start if the goals are met, because if we've got the goals, we can stop there and extract our relaxed plan. Or we can stop if we've reached a point where it's pointless to continue any further, because we keep on adding layers and nothing's changing. So we have another fact layer, and it has the same facts in as the layer before. Then we know that we're not making any more progress, we can stop there. What if we had a pair of actions? So one action is going to, say, increase the value of w by 1, and then another action is going to assign the value v, the function 1 over w. Will the precondition v equal to 0 ever be true? Well, it will at fact layer infinity, but we don't want to have to expand the planning graph that far. So to guarantee that we can terminate the relaxed planning graph expansion, we make this restriction to linear preconditions and linear effects. If you're not working with linear preconditions and linear effects, there's been some recent work by one of our PhD students here, Chiara Piacentini, on using a mixed approach. So if you can come up with an approximation which is good enough for a heuristic, because remember, a heuristic is just a best guess. If you can come up with an approximation and just use the approximation for the heuristic, during search itself, so when you're actually applying actions to your real state, you can link into an external solver to tell you what would really happen. So this problem, we might say, in the heuristic, if we move the tap on the transformer up by one step, that's going to increase the voltage by 0.008. During the search for plan, if we are in a state and we apply the action step transformer up, what we could then do is pass the values of these variables. So instead of saying I'm going to assume it's 0.008, we can pass that step to an external solver which does specialised mathematics, in this case power flow equations, to work out what really happens. So the real plan isn't built on this assumption that 0.008 is the right answer, because it's a rule of thumb, but it's not perfect. But the heuristic can still use that approximation to point search in the right direction. And actually that's often good enough. So the nice thing about this is that you get a plan at the end of it which has been checked against be real power flow equation models using an external solver, but you still manage to use a nice generic domain-independent heuristic by just giving it a linear approximation for the heuristic's sake.